company that deals with highway paving, all right? And we want a particular viscosity level, all right, where we deemed that the flow of the asphalt is not too thick or too watery. Okay? But since we cannot take the whole asphalt and then test it, we are taking samples and then we are testing. But each batch, we want to ensure that the viscosity level is okay, all right? And we are making the point that since we are not taking the whole population, but samples of the population, inevitably there might be some error in what we do. But the thing is whether the error is an acceptable level or not. It's another thing we will discuss later. So let's see, for one sample, okay, so for one sample, we've taken 15 specimens, okay, so we have, let's say, 15 batches in one sample. So the first batch, the viscosity level was 3,193, okay. The second specimen was 3,124 up to the 15th specimen, okay, which was 3,170. So we've taken the viscosity levels for all these batches, right? So if we want to, so for this particular sample, okay, we have 15 specimens within this sample. So if we want to calculate, for instance, the sample mean of viscosity, then, I mean, we have 15 different specimens. So we add all them up and then divide by 15, which will give us 3,210.73. Okay. Now, last week we saw how we calculate the standard deviation. Okay, so here we can take the we can take the particular specimen, compare it with the sample mean, find the difference, square it, and then sum them up, find the square root. That gives us the standard deviation of 117.61. Okay, are we all okay on this slide? Are we okay?
Yes.
Okay, all right. So we've taken, please, yes, is it just coming from one person or let me hear others. Probably just one person understands what we are doing. Let me hear from others. Are we all okay?
Yes, sir.
Yes, sir.
Okay.
Yes, please.
Yes, please.
Good. So, so with the sample mean gives us 3,210.73. All right. And then the standard deviation is 117. So we're going to have something like this. Okay, so the first sample comprising the 15 specimen, we have a mean viscosity of 3,110. Okay, so if we take, normally, if you take enough samples, you should have a normally distributed curve. Okay, so here the mean is 3,210.73, and then we have a standard deviation of 117.61. Okay, so on a particular scale like this, where we have standard deviation to the right, 1, 2, 3, and then to our left, -1, -2. So the -1 is -1 standard deviation to the left, -2 is 2 standard deviations to the left, and then -3 is 3 standard deviations to the left. And so the same thing for your right. Okay, so since this is a sample mean, we do not expect it to be exactly 3,200, okay, because of issues to do with error. But the question is 3,210.73 close enough, okay, to our goal of being acceptable. Okay, the question is, does the sample statistic accurately reflect the viscosity parameter of the overall batch? Okay, so we should be able to calculate this to find out whether it is close to it or it is not close to it. Okay, but the first information that we have, this is how our normal distribution comes out. Okay, all right.
Just one. Okay.
So let's move the argument a bit further. Okay. So after taking one sample, so the first sample is what gave us the 3,210.73. Okay, the sample mean, and then the standard deviation of 117.61. Okay, so this is just one sample we've taken. All right. So after taking one sample, the question is whether the sample mean of 3,210.73 is acceptable. So the best way, right, is for us to take more samples, all right, to see whether we will get similar results. So for the purpose of argument, let's say that we take 9 more samples. Remember that each sample has 15 specimens, okay? So within each sample, we have 15 batches that we take, all right? So out of it, let's say we take a second sample comprising 15 measurements. That also gives us a sample mean of 3,150.13. We take a third sample also comprising 15 measurements, okay? And the sample mean is 3,345.7.54, sorry. To the ninth sample, which gives us a sample mean of 3,023.5. Okay, please, are you all okay with this? We've just made an assumption that we are taking 9 more samples. And for each of the samples, we are being given the sample mean. Remember that this is just an assumption, okay? All right. So basically, this is what we're going to have. We are going to have, let's say, 9 different normal distributions, okay? So each of these samples will have its own sample mean. Do you agree? Okay, so we are going to have, so we have 9 samples. We are going to have 9 different sample means. Okay, 9 different sample means. Okay. So let's say we want to plot what we call a sampling distribution. Okay. This is where we take, we do a plot of, remember that we have this size 9 different samples. So if we put all of them together, okay, all right, we put all of them together to give us one whole, normal curve, okay? This will not just be one sample, it will comprise of 9 samples. In this scenario, we call it sampling distributions, okay? So here, we can, if we want to plot this, we can have, let's say, ranges, okay, for each of the means. Okay, so we have ranges for the means, okay, and then we determine the frequency, of these ranges, and then see the number of items that fall into a particular range. Based upon this, we can plot our viscosity sampling distribution. Okay, so we see here this graph here showing different frequencies for all of the viscosity sample means, okay, for the viscosity levels. Okay, so we get something like this. Okay, right. So when we talk about sampling distributions here, we're talking about so many different samples that have been brought together, okay, and we use that to do our plots, and then we make inferences from this. So this sampling distributions consist of 9 different samples. Okay, 9 different samples. Now let's go on to see other components of the point estimators. Okay, and then we can bring all of them together. All right. We have something we call expected value of the mean. Okay, so here, if we take many random samples from a population with its own sample mean, and then create a distribution based on all of these sample means, the mean of the sample distribution is equal to the mean of the population. Okay, so let me take it again. So we have each sample. Okay, so each sample has its own sample mean. Okay, so let's say we have a population of 100 people, and then we take 10 samples. Each of the sample has its own sample mean. All right. Now, we can take a sample of 20 people, and then all the 20 people will have, all the 20 samples will have each sample, its own sample mean. We can also take a sample of 50 people, okay, and then it will have its own sample mean. Or we could take the whole population. Okay, so if we take the whole population of 100 people, then the expected value, the mean will be the same as the sample mean, isn't it? But the thing is, what is the point in surveying, let's say 100, the whole population, if we are dealing with samples? There's no point. The idea here is that the more samples you have, the closer the sample mean is to the mean of the whole population. Do you agree with that statement? If you take more samples, the sample mean that you will get will be closer to the mean of the whole population. Do you agree? Let's say we have 100 people, we sample 10 people as compared to we sampling 90 people. Okay, so the 90 people will give us a closer mean to the 100 than just 10 people. Don't you agree?
We agree.
Okay, all right. Okay, so the thing is that, so if we take so many random samples from a population, each with its own sample mean, and then create a distribution based on this, okay, the mean of that sample distribution is equal to the mean of the whole population. Okay, so here the expected mean is equal to the mean of the population, that is the mean. Okay, yes, Nene, your hand is raised.
Yeah, okay, good morning.
Good
So
morning.
just a little clarification. In choosing the sample size,
Yeah.
do you have to maintain consistency throughout the whole experiment, or you can vary the sample sizes? So that in the example you gave, the each sample size were 15 members. So the question is, in the other samples you are choosing, is there a way you, I mean, if you alter the members, instead of 15, you make it 20, in other instances 25, are you going to get the same expected mean?
Now, no, it depends. So the sample size will have an effect on our standard error of the mean. We'll come to that very soon. Okay.
Okay, thank you.
All right. Okay. So we have expected value, which is equal to the mean, where the S bar, okay, is the expected value of the S bar, okay. So let's say the sigma and then the S bar, and then the mu is a population mean. Okay, so the expected value, okay, where we take the expected value of the mean, okay, where we take so many samples, should be equal to the ideally should be equal to the mean, okay, that's the population mean. Okay. All right. So this is what I just explained. So the expected value of the sampling distribution of S bar is at best going to be an estimate of mu. Okay, right? So if we take all the samples to match the population need perfectly, then what is the point in taking the samples in the first place? Okay, so the best way is that we find an interval estimate for the population mean. Okay, and then it is affected by the sample size as well as the degree of confidence that we are satisfied with. All right. So the more samples we take, the closer that we get to our population. Okay. And as I just explained, or based upon the question that was asked, okay, the size of the sample also will have an influence on our conclusions. Okay. So let's see. So consider a random sample of n observations selected from any population with a mean mu and a standard deviation. Okay. When Sn is sufficiently large, the sampling distribution will be approximately a normal distribution, where the expected value of the mean is equal to the mean. So if you see your right-hand side, you see the diagrams. The first one at the top. So you have the original population. If you take, let's say you sample, let's say 2 people, okay? And then you go on to sample, let's say 5 people, and then you sample for 30 people, okay? So you see that from 30 going, you begin to have a normal distribution, all right? So which tells you that the more people you have, okay, the better, okay? The more people you have within a sample, the better, because it will help you to have a normally distributed graph, okay? And then in that instance, your expected mean will be closer to your population mean. Okay? And then our standard deviation is the rho divided by the square root of the number of observations. So let's look at the standard error of the mean. Okay. So the standard error of the mean is the same as the standard deviation, but here we are talking about the one for the sampling distribution. Okay, so we call it standard error of the mean. So the standard error of the mean is the standard deviation of the sampling distribution. All right. So rho S bar is the standard deviation of S bar. Okay, the standard deviation, rho is the standard deviation of the population, and n is the sample size. Okay. So let's move on with our example of highway pavement. Okay. So following on with our example on highway pavement, over several years of production and quality measurement, HWP has determined that the viscosity population mean and standard deviation for low noise pavement are as follows. So we have the mu, okay, the population mean to be 3,200, and then we have a standard deviation of 150. Okay. So in this instance, we can calculate the expected value of the mean. Remember that we have 9 samples. Okay, we have 9 samples, and each of these samples had its own mean. So for you to get the expected value of the mean of the sampling distribution, we need to add all the sample means and then divide by 9. Okay, add them up to see if you get the same expected value of the mean that I have on there. Can you add them up and then confirm that the figure that we have here is okay? Can you do that in the next 1 minute, please? Just for you to see how it works. If you are done, you can put it in the chat box. Whatever value you get, put it in the chat box and let's see. Anyone yet? Okay, so Muslim, you had 3,217.08. Okay, anybody else? Okay, good, good. Is Abigail with us? Abigail Aqua. Abigail, I can't hear you.
Nana, yes, please. I'm with you.
Have you calculated the expected value of the mean?
Yes, please.
What figure did you get?
Add 3,217.08222.
Okay, so good. Thank you very much. What about Aku? Aku. Is Aku here with us? I see Aku. Okay, who is Aku? Okay, the last you have a question.
Hello.
Yes.
Yes, please. I got lost, so I'm a little bit I'm lost. Let me put it that way.
Okay, so the last order we are doing is that we want to calculate the expected value of the mean of the 9 samples we've taken. All right. Do you follow that?
Yes, please.
Okay, so for sample 1, the sample mean was 3,210.73.
Yes.
All right, for sample 2, it's 3,150.13. So we've done that for the 9 samples. So if we want to calculate the expected value of the mean, what we do is that we add all the 9 samples and divide by the number of samples. That is what gives us the expected value of 3,217.08. Is that okay?
Yes, please. That's okay.
Okay. So we are all fine with the expected value of the mean. So expected value of the mean here, we are talking about the mean for all the samples we have taken. So it's like the mean of the means. All right. So for one sample, we'll just have one sample mean. Okay. But for sampling distribution, we are talking about a situation where we have so many samples with their corresponding means, and then we find the mean of those sample means. Okay. So this is all that we are trying to do here. So we have the expected value of the mean, which is 3,270. Let's go on to find the standard error of the mean. So remember that we were told in the question that the standard deviation is 15. Okay, the standard deviation is 150. Okay, the standard deviation here is 150. Now remember that for each sample, the batch for each sample is 15. Therefore, the sample size is 15. Do you remember when we started, we said that for each of them, for the first sample, we use 15 specimens, 15 batches for one sample. Please, do you follow? Okay, so,
yes,
so for each sample, okay, we have 15 specimens. So the sample size is 15. Okay, so our N is 15. All right. Therefore, if we want to calculate the standard error of the mean, okay, it is the standard deviation, which is denoted by rho divided by the square root of the sample size, which is 15. So we get 150 divided by the square root of 15, which gives us 38.7. Are we okay with the standard error of the mean? Yes, Muslim.
So why are we not using the 9 for the sample size?
So the 9 is the number of samples. Okay. The 9 is not the sample size. So for each sample, we have the sample size, which is 15.
So we go back to the original sample size, not.
So you go on to the number that you have within your sample for each sample.
Okay.
Is that okay?
Yes, thank you.
So no matter the number of, so in this instance, if we are doing for a sample size of 15, it doesn't matter the number of samples you are taking, but the sample size for that particular one is 15. Yes, Francis.
Hello, Doc. Good morning. Good morning.
Good morning.
Yes. So a follow-up question to what Muslim asked. Why, when we're calculating the expected mean, we did not use the mean that was given in the question. We had to use the mean of each standard to find the expected mean. In the same vein,
What do you mean by we did not use the mean that was not in the question? I don't get you.
when you go to the question, there is a mean of 3,200.
Okay, so that is the remember we are building this up to a certain level. Okay, so that is the 3,200 is the population mean.
Okay, so my question is, the standard error is also the standard deviation of the sample.
Distribution.
Yes, sample distribution. So why don't we go through that, use the sample distribution, the means here, to calculate the standard error instead of going to pick the standard deviation from the question and divide it by the sample size. So that in this.
So we have to do, remember, we haven't finished with what we are doing yet, but we are building up. So,
Okay.
So all that we are saying is that we have a mean and then we have a standard deviation. Okay. But when it comes to sampling distribution, the mean is the expected value of the mean, which is the mean of the means. All right. And the standard error of the mean is similar to a standard deviation for one sample. But here we are looking at everything. Okay.
Okay.
So
All right.
we are building the block step by step.
All right. Okay, that's fine.
Okay. Good. Please, any more questions? Yes, yeah.
Sir, please pardon me. I'm a little bit confused with the standard deviation of 150.
Okay.
Is it within the question or we calculated it from the sample size?
Okay, so the standard deviation was given to us. See.
Okay.
So yeah, we are working with what was given to us.
Okay.
All right, good. Okay, so good. So we know that the size is 15. Okay. Now, this is a situation where we are using a size of 15. Okay. So the error is 38.7. Now, supposing we use a sample size of 135, for instance, just for assumption's sake, okay, we realize that the error reduces. Did you see? When the sample size is increased to 150, the standard error now becomes 6.71. All right. Why do you think it is so? Why do you think it is so? As the sample size increases, the error also increases. The error reduces, sorry. Somebody explain why the sample size is, let's say we started with 15, okay, because we use 15 as for each sample, we use 15 specimen. But let's assume that for each sample, we use, let's say, 135 specimen. Okay, here it reduces to 12.9. And then let's say for each one we increase the specimen to 150. Yes, Francis.
Okay, Doc, I think because the standard deviation is given, the more you increase the sample size, so it means the sample sizes have similar standard deviation. So the standard deviation has to do with the deviation away from the mean. So if all the samples are having the same standard deviation, what it means is they are all close to the mean. Therefore, the error in the sampling will be reducing. I don't know if it makes sense.
You speak like you are explaining this to a lay person. Okay, if you can break it down a bit to a lay person. Okay, if the sample size is 15, I have this error. But if I increase the number of people within a particular sample that I'm doing, the error reduces. Doesn't it make sense that as the number of people you are, let's say you are interviewing more people, let's say 200 people, you interview only 15. The idea, okay, Christina, okay, go ahead. Were you asking a question or answering the question?
I was trying to answer the question, but it seems we are talking, so I have to.
Please go ahead. Please go ahead. I wanted you guys to answer this question.
The more you increase the number of samples you have, the lesser you get error.
So here we are talking about sample size. Okay.
Mm-hmm.
So we are not talking about the sample. We are talking about so in a particular sample, if let's say the number of people, so you are on the same track, okay? But what the slight correction I'm making is that it's not the number of samples. We are looking at the sample size. You can have 20 samples. Each of the 20 samples can have a sample size of 15. In another instance, you can have 20 samples. Each of the sample size could be 135. That means you have more people you are interviewing, isn't it? All right. So the more people you bring into your sample, then the more information you have, okay? So therefore, the error, that's what reduces. I saw somebody raise the hand.
Yeah, okay. Nana, you said what I wanted to say.
Okay, good. So the more people you bring in, so here, the idea is that the more your sample size, the less error you have. Okay, that is why mostly in research, especially when it comes to quantitative research, they want you to have a large sample size so that you can generalize your conclusions better. All right. So we see a relationship between a sample size and then the standard error of the mean. Okay. Right. So the more the sample size, the bigger the sample size, okay, the lesser the error. Okay, good. So here, if we look at the influence of the sample size on the standard error of the mean, let's say where our mu is 3,200, you realize that if n is 15, okay, if n is 15, you see how our normal distribution curve is the one at the bottom, okay? As the sample size increases to 135, okay, it becomes more of a normally distributed curve, all right? Okay. So the values of S bar will have less variation and will therefore be closer to the mean. So which means that the less the number of people or sample size, okay, the further away the values you have will be closer to the mean. If you see the first one, for instance, okay, the one at the bottom, okay, the bell, the first one, okay, the one at the bottom, you see that it tails goes further away from the meal. Please, can you follow? Okay, and then followed by the end where the end is 135, that's the middle one. Okay, it tails also, now when we increase 135, it tails gets closer to the 3,200. Okay, now when we increase it to 500, you see the blue one, okay, the blue normal distribution, okay. You see that it shrinks further inwards towards the 3,200. Okay, so the values within this particular normal distribution are all closer to 3,200 instead of when it was just 15. Okay, so here the main point is that your sample size, okay, has an effect on the standard error of the mean. All right. Okay. So as much as possible, you want to have a larger sample size. Okay. All right. So here, no matter the number of samples you take, okay, you will have the same standard error of the mean because they have the same sample size. Okay. So if you have the sample size, though the expected mean, okay, might change, the standard error remains the same if they all have the same sample size. Okay. So here the sample size is 15, therefore the expected, the standard error of the mean is 38.7. Okay. Are we okay? Yes. All right. So, how do we determine how close a sample mean is to the mean or to the population mean? How do we determine that? How do we determine that? How do we determine that? So you have to understand that the standard error of the mean, like I've just explained, is the standard deviation of the sample distribution. Okay. So if we have the standard deviation of the sample distribution, and then we can also determine the difference between the sample mean and also the expected value of the mean. Okay, we can use to determine how close they are to the mean. We can use that using z-scores. Okay, so we can use z-scores to draw a normal distribution, okay, and determine how close the sample mean is to the population mean. So let's see how we go about that. Okay. So on my left, we said that the acceptable or the population mean, okay, for the viscosity was 3,200, isn't it? Please, do you remember?
Yes, sir.
Yes.
All right. So for a sample size of 15, we calculated the standard deviation or the standard error of the mean to be 38.7. All right. Now, on the x-axis, you see where the mean is. That is, you can denote this by 0, okay, which is equal to the 3,200. All right. In terms of standard deviation, here it is 0. Okay. Now, when we move to the right, one standard deviation to the right, that gives us 1, isn't it? If we move 2, so the 2 on the x-axis is 2 standard deviations to the right, and then the 3 on the x-axis is 3 standard deviations to the right. Now, when we come to the left, okay, -1 is 1 standard deviation to the left, and then -2 is 2 standard deviations to the left, and then -3 is 3 standard deviations to the left. Please, do you follow that? Are we okay with that?
Yes.
Let me have some feedback from you. Okay, good.
Yes, sir.
Now, let's this 3,200, let's put this into figures. Okay, we've calculated that the standard deviation is 38.7. Remember that this is, when we say standard deviation, that means that it is plus or minus 38.7. So on our right, when we move 1 standard deviation to the right, we move 38.71 to the right. Okay. 2 standard deviations to the right. Move 38.7 twice. Please move yourself. We're getting to a very important stage. Okay. So you see that when it was, you see the diagram on my right, when it was 3,200, and then we move 1 standard deviation. You have seen that we added 38.7 to the 3,200. Now for 1 standard deviation, it becomes 3,238.7. Can you see that?
Yes, sir.
Yes.
Okay. So when we move further right, it increases by another 38.7. Okay. And then when we move further right, it increases by another 38.7. Okay, so 3 standard deviations to the right now becomes 3,316.13. So, okay, now it's the same thing to the left. When we move 1 standard deviation to the left, that means that it reduces by 38.7, okay, for 1 standard deviation. When we move to -2 on our x-axis, it reduces further by 38.7. When we move to 3 standard deviations, it reduces by another 38.7. All right, because for each standard deviation, it increases by the value of standard deviation that we have calculated. Okay, so please, do we understand this one, the one on the right? Do we understand that?
Yes.
Does anyone not understand what we have on our right, what we've calculated on the x-axis? Does anyone have a problem with this? I'll go over for you to get a clearer picture. Anyone understands what we have on our right, or both left and right? Are we all with this?
Please go over, please.
All right, no problem. Okay, so let's start with the one on our left. Okay, so our mean is 3,200. Do you understand that? You get that?
Yes, yes.
Okay. Now at the top, okay, at this level, there is no standard deviation. Everything is perfect. So here the standard deviation is 0 because there is no error. What we have is what pertains. So it is 3,200. Now, when we move 1 to the right, that means that now there is deviation from the mean by 1 standard deviation. All right. When we move 2, okay, when we get to the axis 2, that means that we have moved further away from the mean by 2 standard deviations. When we go to 3, that means that we have moved even further away from the mean by 3 standard deviations. Do you follow that?
Yes, yes, please.
Okay, now, in terms, let's put some values to this, all right? So the ones at the top, 1, 2, 3, to the right and to the left, we are okay with it. Now let's see the value at the bottom, 3,200. Let's give a value to the standard deviation, 1 standard deviation. Because we have calculated the standard deviation to be 38.7, okay? If we move to our right to 1, that means that it has, the mean has deviated by 38.7 to the right. Okay, so that's how come on our right, the figure that we have here, we have added 38.7 to it. So now we are getting 3,238.7. Do you follow the first one?
Yes, yes, please.
Okay, good. Now, when we move further away to 2 standard deviations, okay,
Yes,
from 1 to 2, it increases by another 38.7 further away from the mean. Okay, and then it does the same thing for 3 standard deviations. So for each standard deviation that you move to the right or to the left, it increases or decreases by 38.7 for each move. All right. Is it better now?
Yes, please, it's better.
Okay, okay. So we have the same situation here. Here, let's say now we have a sample size of 135. Now our standard deviation is no more 38.7. It is now 12.9. Okay. Now, if you look on the first and the one on my left, the normal distribution on my left, now you see that the viscosity level of a mean of 3,200. Now, when we move 1 standard deviation, now it increases by 12.9. Have you seen that now it has become 3,212.9? Have you seen?
Yes, please.
Okay, so it follows to 2 standard deviations, 3 standard deviations. Now, when we go to our left, okay, first move to the left, it decreases. Okay, so the standard deviation is plus or minus. So when it goes to the left, it reduces by the standard deviation. When it goes to the right, it increases by the standard deviation. So when we go to our left of 1 standard deviation, which is -1, in terms of numbers, it is 3,187.1, which is 12.29 less of the mean. Okay, so we do that to 3 standard deviations to the left, and then we have 3 standard deviations to the right. So now we will have a range. Our range will be between 3,000. Okay, so for a standard deviation of 12.9, if we are doing 3 standard deviations, our range will be 3,161.3 and then 3,238.7. Okay. On our right-hand side, where the standard deviation is 6.71, here we see it clearly on our figures, okay, on the x-axis. So now the standard deviation to the right, 1 standard deviation, it increases by 6.7. So now it becomes 3,206.7 for 1 standard deviation. When we move to 2 standard deviation, it increases by another 6.7, and then we add it to the one on 1. Okay, when it increases to 3 standard deviation from 2 to 3, it increases by another 6.7 and so forth. So it's the same thing for the right, and it's the same thing for the left. Any questions? Any questions, please? Okay. All right. So basically, this is what we have. So for a standard deviation of 0, the viscosity level, okay, see from this one, the viscosity level is 3,000, okay, 200, where n is 15, where n is 135, the viscosity level of standard deviation 0 is 3,200, and also 3,200 where n is 500. Okay. Now let's take the first row where n is 15. Okay, we've seen it already in the graph. If we go standard deviation 1 to the right, that will increase by 38.7. Okay, to the right even further, it increases by another 38.7. Okay, now where we have sample size of 135, this is the same thing. Okay, here our standard deviation is 12.9. So to the left or to the right, for each move, it increases or decreases by 12.9. If you go to the right, it increases by 12.9. If you go to the left, it decreases by 12.9. Okay, where the standard the sample size is 500. Okay, our standard deviation or standard error of the mean is 6.71. Okay, so if you start from 0 where it is 3,200, you move to the right, it increases by 6.71. Okay, you move to further right, it increases by another 6.71. Okay, when you move to the left, it decreases by 6.71. Okay, so you see that the decrease is 3,200 minus 6.71. That gives us 3,193.3 and so forth to the third standard deviation. Are we okay with this? Are we okay with this table?
Yes, sir.
Good. So let's see how close this will be to our population mean. So you see that for each, so for the mean S bar to 3 standard deviations to the left or to the right, okay, is what we have here. So you can see for N, for where N is, who can explain the first one? So where S bar is plus or minus 3 standard deviations, N is 15. Why are we getting 116.1? Can somebody explain why?
Hello, Nana.
Yes, please go ahead.
I think that is the difference in the Z-score. As the Z-score moves to the left or right, whether positively or negatively, it is moving by a difference with the mean of three steps now. It's moving with a difference of 116.1 to the left or right.
Okay,
So you will see that from the point 0, which is the mean of the population, to the point 3, you would see there's a difference of this figure, 116.1.
All right. Okay. 116.1. Okay. So how do you explain that for the so another way you could okay. But well done. Let me hear from the last yes.
From the formula, I multiply the standard deviation by 3.
You multiply the standard deviation by 3. Okay, so
Yes,
if you well done. So if you multiply, so let's say we want the third standard deviation. Okay, all right. Okay, so we multiply the standard deviation is 38.7. So if you multiply 38.7 by 3, you get 116.1. All right, so that will be to the left or to the right. That's why we have negative and then positive. Okay. All right, so the same goes for where the size of the sample is 135. Okay, we multiply 12.9 by 3. Okay, so it's the same explanation as we had at first. Okay? And then where the sample size is 500, we multiply 6.71 by 3, and then it gives us the range. Okay. Any questions? Any questions so far? Any questions so far? Okay. All right. Okay, so what's the time now? Okay, would you like to get something to drink? Let's go for 10 minutes and come back, okay? Get some hot
Okay,
drink.
sir.
Okay, Nana.
Please.
Let's come back 9:30. Okay.
Thank you, Nana.
Thank you.
In the meantime, I'm here. So if you want to, anybody wants to ask a question, you can do. Yes, Pius.
Good morning, Anna.
Good morning, Pius. How are you?
Fine, fine. So my question is from the previous class.
Yeah. Okay.
Yeah. So when we were comparing the results we got to the Z-score, the sheet for the Z-score,
Yeah.
I noticed we took the Z-score from only one of the lines. Why did we not go to the next one or two lines in that order?
Well,
Why did we?
Is it this slide? Which one? Which one are you referring to?
Not this slide. It's from previous class.
Okay.
So
Previous slide.
my screen.
This one.
Not this unit. Last Sunday.
Okay. Last Sunday. Okay. You sure when
the Z-score. We took it from only one of the lines because so let's say maybe the negative Z-scores, we have multiple columns. So there is the first column, there is the second one, there is the third, fourth, fifth. But we took the score from only the first column.
Okay, so what I will do is that today to do another Z-score, I'll explain why. Okay.
Okay, thank you.
All right. Have calculated here. Okay, so we can know the how do you call it, the standard deviations, all right? And we said that if we want to see how close our figures are getting, we are getting is to the population mean, we can use Z-scores to determine that. So let's see a particular example of how this can be applied. So we want to find the probability of sample proximity, okay, how close a sample is, okay, to the population mean. Now, for each of the population sizes, what is the probability that the sample mean is within 15 of the population mean of 3,200? Okay, so here we want to find whether in a range of plus minus 15 of the population mean of 3,200. Okay, we want to find a value and then determine its probability to see whether it is close enough or not. Okay, so here we have a range of 3,815, that is 3,200 minus 15, all right? And then the upper value is 3,215. Okay, so we add 15 to this and then we deduct 15 from the mean. So that's what gives us the upper value and then the lower value. So this is the range, okay? So So basically, we want to find a range where it's between a range of 15, all right? Between 3,185 and 3,200. So we want to calculate this. All right? Okay, so let's see how we go about that. So we know from our calculation that the upper value is 3,215, and then the lower value is 3,185. So let's calculate the z-score for the upper value. Okay, so here we have the z upper. All right, so the upper value is 3,250. Remember that our mean, okay, all right, is 3,000 for the whole population is 3,200. So per what we've learned already with the z-score, we deduct the mean from the observed value, and then we divide that by the standard deviation. Okay, so here our standard deviation is the standard error of the mean for this sampling distribution, which is 38.7, which we have here, 38.7. And then our z upper is 3,250 minus 3,200. That gives us 0.38, okay, 76. Okay, now let's see that for z lower, we use the lower value, that is 3,185 minus 3,200 divided by the standard error of the mean, that is 38.7. That also gives us negative 0.3876. Okay, right? So let's see the z values, okay, for the upper and then the lower. Okay, so let me share. Let me share my, let me share my z table. Okay, just a minute. Let me share my. Give me a minute. Okay, let's try this. Okay, so we have our z upper to be 0.3876. So let's see that from our z table. Okay, 0. So let's make it approximately 0.39. Okay. So when we come to our Z table, please, are you all seeing my Z table?
Yes, please.
Yes, please.
Yes, please.
So for you remember you asked a question about how we read the table. So let's see how we can read the 0.39. Okay, so on the Z column, okay, you move to where we have 0.3. That is the first figure. Okay, and then the second one is 9, isn't it? 0.39. So we want to add 0.09 to this to make it 0.39. So we go to the 0.09 column, okay? And then we move to here, okay? The line that corresponds to the 0.3, all right? So the Z-score for the figure that we have for 0.39, the probability of getting this is 0.6517. Pius, do you understand how we read this?
Yes, Nana, thank you.
So we have 0.617. So let's go back to our slide. So the one for the upper is 0.617. Okay. Now let's see for the lower. The lower is negative 0.39. Okay, so let's go back to our table. Okay, so now that one is a negative figure. So let's go to the next one, which is negative. We move to where we have 0.3. And we have 0.3. So negative 0.3. Let's go down a bit. So we have negative 0.3 here. We know that the last column is 0.09. So this is where we have negative 0.39. So here the probability for negative 0.39 gives us 0.3483. Okay. So that will be our probability. Okay, so we have the probability for the upper and then the lower. Okay, so the range of probability, okay, you deduct the lower from the upper, that gives you 0.302. All right, 0.302. Okay. So the probability that a value will fall within 15, okay, of 3,200 is 30%, is 0.302. Okay. All right. So the probability that the sample mean for n is equal to 15 is within plus or minus 15 of the population mean is 0.302. Any questions about this?
No, please.
Yes.
After finding the probabilities of the two upper and lower, you just find the mean between the two values to get a 0.302. I just want to
so I didn't find the mean. When you find the probabilities, so these are the probabilities. Oh. 0.617, okay, 0.6517, okay, and then the one for the lower is negative 0.3483, isn't it? So you just find the difference, and that gives you the probability of the range between the upper and the lower. Yeah.
Thank you.
So that's what we have here. So the range between the upper and the lower, the probability that you will pick is within that. Okay, so this is the estimate that tells us that it is close or it is not close. So 30% probability is less than a fair point toss. So it's really really small. Yes, Nancy.
Nana, could you please go to the other slide where we calculated the probability?
Yes. You mean the Z-score table?
Yes.
Okay,
I'm okay with the table.
So we calculated.
Okay, so Nana, we were picking these figures from the Z-score table and then deducting the lower from the upper to get the 0.302.
Yes. Better now? Is it okay?
Yes, that's okay. Thank you very much, Nana.
Yes, Archie.
Yeah, Nana, please, I just want to get some clarification here. We are supposed to deduct the lower from the upper. Is that not the case?
Yeah.
So let's say upper minus lower.
No, don't think around that. So we are not going to add it to say negative times negative. So I see.
No, I just wanted that clarification so that I am.
If it is.
So are we using the absolute values?
No, we are taking the probabilities from the table.
Yeah.
So if it is negative, then I mean that is a range. So you add it. So in natural sense, you are deducting it.
Okay, that's what I want to get.
Okay, all right, okay, good. Any question? Yes, actually your hand is still raised. Yes, Muslim.
Okay, Nana, when I did the subtraction, the 0.6517 minus 0.3483, I'm having 0.3034. Is that going to be a problem?
Oh, this is an approximation. You see the sign here. It's an approximation.
Okay.
Here. Any other question? Remember that we approximated to 0.39 instead of using 0.3876. So, yeah. Any question about? So now you see that with Z-score, we are able to calculate how close a particular value is to the mean. Okay, so here 30% that a value will be within 15 of the viscosity level. Okay, so which is a very low probability. Yeah. Now, where our sample size is 135. Okay. Work out to see whether you will get the same probability of 0.755 based upon what we've done already. So now the sample size is 135. And then the standard error of the mean is 12.9. Okay, so based upon what we've done, find out that the probability or the probability of a value, okay, of the sample mean being within 15 plus or minus of the population mean. Okay, so work that out. So now find the upper, Z upper, find the Z lower, okay, and then deduct, go to the table, draw out the probabilities, and then see if you have the same figure I'm getting here. Okay, so 5 minutes, let's all do it. Michael, please go ahead.
Thank you, Nana. Please, the 15 that we are using, sorry for taking back. I want to understand why we are adding 15.
Oh, it's just a question that was asked. It's just a random number that was picked, that's all.
Okay.
Okay, so please go ahead and work it. Michael, if you could put your hand down, yes. Please go ahead and work it. If the population size should change to 135 and the standard error of the mean now becomes 12.9. Okay, I want you to determine the probability that the sample mean for n is equal to 135 is within 15. I want you to work it and see if we will have the same answer. If not, we'll find out why. Please, if you are done, you can indicate it in the chat. Anybody yet? Yes, anyone yet?
Hi, Nana.
Yes. May I
Please,
know the one
I'm
speaking, please?
getting, this is Nancy.
Nancy, okay.
Yeah, so I'm getting 0.754. That is 75.4%
Okay,
probability.
good. Brilliant. Okay. 75.4%, yeah? Okay, probability. Okay, good. Can you take me through how you did it?
Yes. So for Z upper, we are deducting the population mean from 3,215 and dividing it by the what's it called? Is it the mean for this sample size 150 135? Yes. So that gives us
what is the numerator? What do you have at the numerator? So
numerator 15.
For the upper was 15.
For the
no?
upper, yes. So 15 divided by 12.9.
Okay.
And I got 1.16.
Okay.
So for the probability from the z-score table for 1.16, I got 0.8770.
Okay.
And then for negative 1.16, I got 0.1230. So deducting the lower from the upper, I got 0.754.
All right, good. Please, can somebody also share his or her work, like take us through how you did it? Yeah? Any volunteer? Okay, yeah, go ahead.
Nana, please, mine will be a question after somebody shares this.
Okay, all right, okay. Any volunteer? Melody, I see that you worked yours. Can you take us through how you calculated it?
Hello, Nana.
Yes, Melody.
Please, it's basically the same as what Nancy just mentioned. So the Z upper, I got the 15 divided by the 12.9, and I got 1.16. And the Z lower, I got negative 15 divided by the 12.9, which I got the negative 1.61. So reading from the Z table, the 1.16, when you read it, you will get the 0.8770. And the negative 1.16, you get a negative 0.123. So when you do the subtraction, you get a 0.754.
Okay. All right. The last thing, yes.
Yeah, so I wanted to be clear. When you're finding the Z upper, the denominator is the 12.9 rather.
The error of the mean, yes.
Oh, okay. Thank you.
Okay, good. Excellent delivery. Good. Okay, so it will be the same. Oh, yes, yeah, you wanted to ask a question.
Yes. Nana, please, can we go back a slide to where the cumulative calculation
is?
One slide back. I think 2 slides. Here. So, with what Achu asked earlier on, with the negative thing, I just wanted to get it. When we say cumulative, we are adding the two. So, with this particular one, I was thinking back to the initial studies we did, where you said when you have a similar negative z-score and a positive one, when you add them, you get 1. In this case, we are not adding the probability of the two z-scores. We are subtracting the upper one from the lower one.
Okay, put it this way to make it simpler so I don't get confused. As you said, cumulative, we are adding, isn't it? One is negative, one is positive. Okay. Is it not so? Oh, you've gone.
Yes, sir.
So one is negative, one is positive. Okay. So when you add the two, you get the range. The main thing is that one is to the left, one is to the right. So you want to find the probability of the two. Okay. So you just find the how do you call it? And this cumulative that we are talking about is, we have one for the upper, we have one for the lower, and we want to find the range. That's all. Okay, so don't get yourself confused too much as to how do you call it? Remember, this negative 0.38. When you find the probability, what do we get? The probability, what is 0.38. 348 isn't it?
Yes, sir. 348.
Then you deduct it from the. So you don't. I mean, if you add it, how can that be the range?
So that's what I wanted to clarify it. Because how the way cumulative makes it feel like you are adding it.
So here the cumulative is for each of the probabilities, for the upper and then the lower. And we want to find the range of these
between the two.
All right.
Okay. Makes sense. Thank you, sir.
Okay. All right, so we have the same situation also for 500. I'm sure you all now know how to work it out. Okay, so you do one for the upper, one for the lower. All right, and then you draw the, you find out the difference, okay, and then you pick up the probabilities from your Z-score table. Yes, the last.
I'm working out the previous one and I'm not getting the same ones.
Okay, so you're working on this one?
The 130, yes, please.
Okay, so let's go through it together. Let's go through it together. Okay, so.
Okay, so please, should I say my, or they are coming to help me?
You say, okay, go ahead.
For the Z upper, I did 3215 minus 3,200 over 12.9. Please, isn't it?
Yes. So the 3,200, the difference gives you what?
It's 15.
15, okay, divided by
12.9.
Yes. Okay, so what do you get?
Yeah, I got 0.1627.
0.1627. Okay, please, did you all get that?
No.
No, it's 1.1.
Hey, sorry. 1 point. Oh, okay. It's 1 point. Okay, thank you. I've seen my mistake.
All right, okay, good. All right, okay. Any other question? The last, you kindly put your hand down. Any other question? Okay. All right. So you can see, okay, you can see that when the population size increased, okay, when it was 15, okay, and they wanted to find the value between those within 15 of the viscosity. Okay, yes, Nancy.
Sorry. What I understand why there's the inverse relationship between the population size and then the mean is it mean error?
Standard
I
error.
understand, yeah, the standard I understand, but why is it that as the population size is increasing, it's like the probability of the mean also keeps going up?
The probability, okay, so see this one. Let's see this. That's a good question. So you see that the first one, the probability was 0.302. All right. All right. So when we increase the population size, okay, now you see that the standard deviations also, the standard deviations reduced, didn't it?
Yes.
So the standard deviation between the two now was for how do you call it? For the first one, 12.9 to the left and then 12.9 to the right. Okay, please, are you following?
Yes, sir.
Okay, now when we calculated the probability, okay, the probability now was 0.755. And then when we even increased it further, the population size further, okay, to 500. Now you see that now the it includes more people. Have you seen? So now the probability of you getting closer to your mean is higher. So you see that when we increase our the sample size, we get a very low error as compared to when it was just 15, it was this. But when we see that everything was within this range, everything outside this range will be rejected. Okay, we'll come to our testing very soon. Now, when we came here, you see that it enlarged a bit. All right.
Yes.
So now it's accommodating more.
Yes.
And then, so the error here is lower than when it was 15.
Yes.
Okay. So when we increase it to even 500, you see that now it's going to the tip of the curve. All right.
Yes.
So you see that it's accommodating more. So here it's even very low error. So it makes sense. So as you increase the sample size, the probability of making a mistake reduces. Okay, therefore the probability of picking the right one increases. Isn't it?
Nana, please, this distribution is for the entire population, right?
Yes.
Okay.
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 This is for the entire population. All right. All right. Okay, any other question? Any other question? So the sample size has an effect on the probability. So as you increase the sample size, okay, then there is room for less error and high probability of a figure being chosen. Okay. Any questions?
Yes, Nana, one more question, please.
Go ahead.
So I understand it's good to have a large sample size, but should you also necessarily have many samples? What I mean to say is from what we are doing with the figures we work with right now, it's better to work with a sample size of about 500 per sample, 500 specimen per sample.
Yeah.
So since we haven't 500 specimen in each sample, do we necessarily have to have like 100 samples, or we can just work with 2 and then have each sample be 500 specimen? Or is it that because we are having 500 specimen in each sample, we should have about 100 samples?
So remember that for each sample, the sample for one sample, it will have its own sample mean. Do you follow that?
Yes, so, yes. Each sample will have its own sample mean. True.
The larger the sample size, the closer you are to that sample mean. Is that not it?
Yes.
Now, if we have like in the case of the highway paving, we have continuous production of asphalt. Okay.
And
then we just pick just a few samples as compared to a situation where we can pick so many samples. Okay. All that we are seeing is that situations where we pick so many samples, we are better at getting to the population mean than when it was fewer samples. Okay, so
the samples.
Yes, so you can just pick one sample, increase the size, that is well and good. Okay, but if you increase the size and then you have so many other samples, it's better than just having one sample where you have increased the size. Is that not it?
No.
Okay, so
Nana, is it the specimen within the sample or the number of the samples itself?
so we can do one sample size at a time, isn't it?
Yes, yes.
We can do one sample size at a time. So if the sample size is, let's say, 15, okay, all right, we can do one sample, two samples, three samples, 100 samples. Once we stick with the 15, then everything is 15 for that particular one.
Of course.
Okay, so in that sense, the 15 is a constant, all right? Okay.
Okay.
Now, let's say we have the opportunity to do one sample, okay, when the n is 15. We have the opportunity to do 10 samples when n is 15, okay? In these two, which one do you think will be? Remember that the n in this particular instance is the same. Okay, so within these two, which two do you think will give us closer, how do you call it? Closer.
The 15.
Oh, no, see.
The 15 compared to the 10. Oh?
No. See, for sample 1, n is 15. Okay, if we do one sample, n is 15. Let's say we have different cases. Let's say case 1, okay? Let's say case 1, where n is 15. Where n is 15, we can do one sample, so n is 15. Okay, you get that one?
Oh, n is the size of the sample, not the number of samples.
The number of samples, it's just the size of the sample.
Okay.
Okay, so there is a difference between the size of the sample and then
yes, the number of the samples.
Yes.
I
Okay.
think that makes it a bit better.
Okay, so that's all I will be saying all along. That there's the size of the sample, and then we have the number of the samples. These are two different things.
So the size of the sample is what to look for, like ideally.
Determining the standard error of the mean, then we look
To
at
determine the standard error of the mean error, the size of the sample is ideal.
Standard deviation.
All right.
Okay.
All
right. Okay. Good.
Thank you very much, Nana.
The last thing, yes.
Please, I needed assistance with regards to how do I put it? Rounding up decimals.
Okay.
Yes. So I wanted to know whether we are to when the number is higher than 5, you add 1 to the previous one. Are we to do that in this case, like for the z-score?
In this case, most of the things I did here, I used the computer to do it. So, but if you are reading from the table, remember the table just gives you 2 decimal places. Yes, so just run it up to 2 decimal places and work with it. It's fine.
Okay, so Nana, the z upper for the 500 distance.
Yes.
What is it called?
Yeah.
I had so for z upper, right, I had 2.23880 blah blah blah. So to round it up to 2 decimal places.
Just a minute. You have
2.23880.
2.2388. Okay.
Yes.
So for your z upper. And what did you get for z lower?
Negative 2.2388.
Okay. 2388. So when you are going to your table, okay,
Yes.
Just do it 2.24.
Okay.
And then you take it from the table. Okay?
Yes, please.
So you go to where the 2 column is, okay, and then you work it out. If that is not going to work, you can do it 2.2, okay, and then you pick. So depending, so let's go to the z table together.
Okay.
Okay, so let's pick 2.23. So we have 2.3 here, isn't it? For the lower, we have 2.3 here. Okay. Sorry, 2.2 here. All right.
Yeah, I've seen it, please.
So we'll go to the fourth column. Okay. So you can have 2.24. Okay. Then you come to 2.24. That should be 0.0125. Yeah. Okay. Good. All right. Please, any other question? Yes, Michael.
Yes, sir. Please follow up to the question that the question was in terms of the sample size and the samples. So let's say we have 15 sample size and then the samples are 10, that would be 150. Is it possible to have 2 samples with 75 sample size and get the same answer?
No, please, one at a time. You say you have a sample size of 15.
Yes, and then the samples are 10.
And then the samples are 10. Okay.
Yes. Automatically means that you are going to have 150.
Why are you going to have 150?
Because if the samples are 10, it means that every sample will have 15.
Every sample will have 15. So this 150, what are you referring to?
The sample size for the 10 samples.
So the sample size, listen, the sample size for the 10 samples is 15 for each of them. That's all. It stays 15 for each of them.
Okay, so what I'm trying to say is that together it will be 150.
No, you don't multiply it to be 150. The sample size, see, the sample size, let's say the sample size N is 15. And then you are taking 10 samples. All right. These samples, each of the samples will have its own sample mean. Okay. Each of the samples will have its own sample mean, but each of them will have the same size.
All right.
50. Is that okay?
All right, sir.
So what we are doing, we are finding the mean of the sample means. We are finding mean of sample means. So don't let the sample size pertains to each of the size of the sample. So if we have 10 and where we say N is 15, then sample size is 15. We take another sample 2 is 15. Third sample, N is 15. So the N stays the same. All right. Okay.
But my question is that if we have 2 samples, for which each one also has a sample size of 75, and then we want to find the mean of the 2, will the 2 mean for the 10 and the 2 be the same, or there may be variations?
I can't hear you properly.
So what I'm saying is that if we have another sample with a sample size, 2 samples with a sample size of 75.
So let's say you have another sample size of 75. Okay. And then you want to compare it with the one that is 15. Is that what you're saying?
Yes, so the 15 we have 10 samples. And then the 75 we have 2 samples.
Okay.
So what I mean is that if you check the sample mean for these 2, would it be the same?
Of course, it will not be the same. It will not be the same. So you have to determine. So remember that everything that we are doing is in relation to how close they are to the population mean. Is that okay? Hello?
All right, so I can hear you.
I'm not getting the feeling that I'm getting through to you.
Yes, please, you are getting through to me. I can hear you.
No, I'm saying that, no, I'm saying like you understanding what I'm saying.
Yes, please. Yes, please.
Okay, so if you have N is equal to 75, and then you pick 2 samples, that is entirely different from a scenario where N is 15 and then you are doing 10 samples. All that we are saying is that for N is equal to 75 with 2 samples, if you do another N is equal to 75 with, let's say, 5 samples, you will get a closer you get a closer value to the mean than when it was just 2 samples. And then when you take n is equal to 15 and 10 samples, and then you compare it to n is equal to 15 with 3 samples. Comparing the two, okay, the one with the 10 samples will give you a closer value to the mu than when it was just 3 samples. That's what we are saying.
I get it.
Okay, so don't mix them up when n is equal to 15, 10 samples, and then n is equal to 75, 2 samples. Okay, just stay within one category, and then, because you can do one at a time. Okay, all right, good. Please, any other question? Any other question? Okay, yeah, definitely.
Please, I wanted to know what's the difference between a sample size and the number of samples.
Okay, so a sample size is, let's go to the first example that I gave. Okay, so this was our first example. Okay, so for each sample, all right, let's say when the production reaches a certain level, we pick a sample, but that sample consists of 16 specimens. Okay, so 16 specimens in the sense that, okay, let's say we have batch 1. Okay, batch 1, within this batch, we have 15 specimens. Okay, so this is just one sample, but the sample has various specimens to it. So it's like you can see it like, let's say, a sample within a sample. Okay, all right. So this is just one sample, and then for each of the samples, each of the specimen, we get the viscosity level for the 15. So if we want a sample mean, remember this whole 15 is just for one sample. So if we want a sample mean for this whole stuff, then we add the viscosity level and then divide by the number of specimens that we have. That is what gave us 3,210.73. Are you okay with this one?
Yes, please. Yes,
Now,
please.
what about a situation where we do so many samples, like we take 9 samples, and each of the 9 samples has 15 measurements of each. So the first sample that we took gave us a sample mean of 3,210. Okay, so we do a second sample, also consists of 15 specimens. That's the sample size. All right. Yeah. So we do another one, and then it gives us another mean of 3,150. Okay. We can do a third sample, also consists of 15. So these 9 samples that we have, each of them consists of 15 measurements with a sample size with their own sample sizes. Does it make sense?
Yes.
Okay, Now, we are building upon this to something else. So where we have a sample distribution is when we are taking all these samples and finding the mean of all these sample means. Okay, so that's what leads us to this. So we have sample 1, sample 2, sample 3, up to sample 9. All of them have their own sample means. Okay, and then we want to take a mean of all these sample means. That's all this sampling distribution is about. Okay.
Okay.
So that's what leads us to this, where we have the sample mean. So that's what we are saying, that the expected value will be equal to. So as you take so many samples, then you get closer to the population mean, okay, than taking fewer. So that's what this whole thing is about. Yeah.
Okay. So please, my question is, if okay, so now I understand the sample size, but I mean, what's the difference between that and then the number of sample? Like, I don't know if my question is clear or.
Okay, so let's say you can take one sample and then the sample size is say 15.
Mm.
And then we do 10 samples. Okay, so each of the 10 samples, each of the sample will have a sample size of 15. So that is the sample size. And then the
Yes.
number of samples is, you know, so each sample will have a sample size of 15. And then we can take so many samples. Okay, now we can decide to have a sample size of 20.
Okay.
Right? When we take a sample size of 20, that means that for one sample, now the sample size is 20. Now, when the sample size is 20, we can take, how do you call it? We can take, let's say, 50 of those samples. So now, each of the samples will have a sample size of 20, and the number of samples will be, let's say, 50. All right? So each sample, so the sample size is like the number of specimens that you have in each sample. So let's say I want you to interview some people. Okay. Now I pick 3 people. I pick one person. Let's say I pick you. Please, what's your name? I can't see your name because I'm sharing. So
I'm Stephanie.
I pick Stephanie. Stephanie,
Yes.
go and let's say 50 people. Okay, I want to do some
So, Nana, please, does that mean that the number of samples it can be, you can choose the number of like samples you want to work with? So it's not fixed. It's not like something you need to calculate or work for. So you can estimate that you just want 50 number of samples or maybe 100 number of samples.
Yes. So let me give a practical example. So let's say I choose Stephanie. Stephanie, go and interview 50 people at random on KNUST campus.
Okay.
All right. So now, in this case, Stephanie will bring observations for 50 people, isn't it? So
yes, please.
So the sample size is now 50, isn't it?
Yes, please.
Okay. All right. Now, per the results you bring, probably management will base upon that to make some decision. Now, let's say I choose Stephanie, and then let's add Ransford to it. Okay. So Ransford, you go and interview 50 people, okay, on campus. Now, I will get 2 samples within time. We'll get two reports. That is
yes,
you
please. Yeah.
But we are all interviewing 50 people.
Yeah.
Now I take the whole of analytics class. Everybody go and interview 50 people. Okay, let's say now you people are about 50 something. Now I'm going to get 50. Each of you is going to give me a report for 50 people. Is that not it?
Yeah.
All that we are saying is that the results that I will get, if I should send 50 people, I will be able to get more, because let's say we don't know the population of KNUST. All right, let's assume that we. Now, the result that I get from 50 of you guys, okay, wouldn't it be closer to what the students are saying than just relying on when I send only Stephanie to do 50 people? If I get 50 people bringing me 50 results each, as compared to just sending Stephanie, who will just give me 50 people.
Yeah.
Then the result that I will get for 50 people of a sample size of 50 will give me more insight than just the one that I send only you. Is that not it?
Yes, please.
That's what we're saying. So here, the sample size is the 50. Okay, the number of samples is the number of people I send to go and then bring in the information. So here the number of
Okay.
samples will be 50 something, that's your class size. And then each of
Okay.
you bring me the 50 people you have interviewed.
Okay.
Okay, does it make sense now?
Yes, please. It makes sense now. Thank you.
Good. So, thank you. So let's move on to what's the time? I want us to finish this and then. When do we normally go for your break?
Mm-hmm. 12 to 1.
Okay. Let me see. Let me see what we have, and then when we can go for our break. But are we all okay so now? Okay. All right. Okay. Let's go for a break. When we come back, then we will continue from sample proportion. Okay. Why don't we, because we have a long day, why don't we finish? If you are okay, we can finish with this, and we go for our main break, and then we come. What I'm saying is that we can take this in chunks and then finish earlier. I don't know.
I think it will help because we've gone for about 15 minutes already.
You say?
That would be fine.
It will help because we've gone for 15 minutes.
Yeah, so let's continue with this, and then when we get to a place, let's say when it's about let's now, what's the time now? So let's say when it's okay, I will decide. Then we can go for a long break and then come back, and then we start another unit. We take it off from there. Yeah. Okay. So
Yes, Nana.
okay. So let's see sample proportion. Okay. So this is similar to the example that I gave. So let's start with this illustration. So the administration of Analytics University is considering adding a Moonlight Cafe to the chain of restaurants on campus. Okay. The cafe will have drinks, snacks, comfortable furniture, and plenty of space. Okay. To learn more about the student interests, administration hires a BDA graduate student to go out on campus and survey 30 students. So the question is yes or no. Would you like to study at Moonlight Cafe at least once per week? The result is that 17 out of 30 students answer yes. Okay, so basically what we are saying is that the result of this study, okay, is a sample proportion. Okay, so we are interested in those who will say yes for us to add the Moonlight Cafe. So 17 people out of 30 said yes. So the proportion is 17 over 30. This is the sample proportion. Okay. This is a sample proportion. So we count the observations in a sample that we are interested in. In this case, we are interested in the yes, and the number of observations in the sample, which is 30. Okay, are we okay with this one? So where we want the sample proportion, that's the P bar, is X over N, where N is the count of observation in a sample in our variables that we are interested in. So here we are interested in the yes response. Okay, therefore, our sample proportion will be 17 over 30. Are we okay with this?
Yes, Nana.
Okay, good. So that gives us approximately 56.7%. Okay, 56.7%. Okay, so that's our sample proportion. Now, sample proportion is similar to that of the sample mean, okay? But it's similar, but it's not the same, okay? So a sample proportion represents what is essentially nominal, that is usually binary variable. So here we are interested in where we have a binary response, yes, no, true, false, agree, disagree kind of thing, okay? So it is a count or frequency of the nominal variable of interest, okay? So normally related to binomial distribution. Okay, so here, where you are dealing with a situation where you have yes, no, agree, disagree, kind of true, false kind of scenarios, then we use more of sample proportion. Okay, so the expected value of the sample proportion denoted by P, okay, is the mean of all potential values of P is equal to the population proportion. So just as we have sample proportion, we have population proportion. So the population proportion relates to the entire population, okay, whilst the sample proportion relates to only the sample that we've taken. Remember that when we talk about sample proportion, we are only looking at things that we are interested in, okay, things that we are interested in, okay. So we refer to the standard deviation of the sample proportion as the standard error of the sample population, okay. So here, the terminology is a bit different. The only difference here is that the standard error of P is dependent upon whether we are dealing with a situation where the population of interest is finite or it is infinite, okay? So what we are really asking is the sample size large or small in relation to the population? So for instance, if we are taking a sample of 15 from a population of 200, are we taking it from 200? Are we taking it from 20? Are we taking it for 2,000 and so forth? Okay, so most of the time we assume that the population is infinite. We don't know, okay, in relation to the sample size, and that affects the way that we calculate our standard error of the sample population. Let's have it. So where we know the population, then our standard deviation, okay, our standard deviation becomes the population that we know, okay, minus the sample size all over n minus 1, as the population minus 1. You find the square root, and then you multiply that by the proportion of what we know, what we are interested in, multiply by the one that we are not interested in, 1 minus p, all over the population size or the sample size, okay? But where we do not know the population, then we use the one on the right to calculate the standard deviation or the standard error of the proportion, okay, which is 1 square root of p into bracket 1 minus p over n, okay? So basically, if another way to look at it is when you know your n, that is your population number, okay, and then your sample, and then it is less than or equal to 0.5, use the finite population calculation, okay? Where it is more than 5, we use the correction factor. Okay, so let's see. So for a normally distributed data set, okay, your population will be the standard proportion will be p bar minus the expected proportion divided by your standard error. And here we denote the standard error as the proportion into bracket 1 minus p over n. Okay, we'll take a particular example and then you see. So let's put some figures to this so that you understand what we are saying. The same example, okay? Now, the administration of Analytics University is considering adding a moonlight cafe to the chain of restaurants on campus. The cafe will have drinks, snacks, comfortable furniture, and plenty of study space. To learn more about the student interest, the administration has a BDA, Big Data Analytics graduate student, to go out on campus and survey 30 students, right? Yes or no? Would you like to study at Moonlight Cafe at least once per week? The result is that 17 out of 30 students answer yes. So, like we've just demonstrated a while ago, our sample proportion will be 17. That's what we are interested in, not the other 13. Okay, so it's 17 over 30. That gives us approximately 56.7%. So if we want to calculate the standard deviation in this case, then, or the standard error, it is 56.7, that is the P, okay, into bracket 1 minus P. Okay, so 1 minus 56.7, all right, all divided by the number of people we interview. And that gives us a standard error of 0.0905. Okay, are we okay with this one first before we build on this? Yes, the last one.
Yeah. Please, I wanted to be clear on whether we are to use the 0.567 or the percentage rather.
All of them will give you the same thing. So 0.567. It's the same thing. If you are using percentage, then make sure that everything is a percentage. Okay. All right.
Yes, please.
Okay. So 0.567 into bracket 1 minus 0.567. Okay, gives you over 30, gives you 0.0905. Okay. Yes, any other question? The last, your hand is still up. Yes, Achu.
Yeah, Nana, please, I just want to find out. We calculated for P bar, and we are using P. So I want to be clear.
We calculated for
P bar.
Yes. So
and then we are using P, yeah.
So calculating for, so that when we calculated the P bar, okay, we got 56.7.
Yeah.
Now to calculate for the standard deviation. Okay. So it is the P that we have calculated, or the P bar you have calculated. Okay. All right.
All right.
That is 0.567 into bracket 1 minus P. Okay, over this. Okay, so in this sense, the P is the same as what you calculated for your P bar. Yeah.
Oh, okay.
Okay. All right. Please, are we all okay up to this point? So we know the standard error. Okay. We know our standard error. So once we know our standard error, okay, once we know our standard error, remember that our standard proportion is 0.56. So once we know our standard error, that means that it can be to the right or to the left. Remember, as we deal with standard deviations, it's the same thing. So if our standard error is 0.0905, then when we go to the right, you just add 0.0905 to 0.567. That will give you standard deviation to the right by 1. Have you seen? And then it increases by each unit. Okay, so for each unit, it increases by 0.0905, just as we did in the past. So you do that for the left and also for the right. Okay, are we okay with the diagram? So now we have our sample proportion. Okay, that is the people we are interested in. Okay, it's 0.567. all right? And then we've calculated our standard error, all right, to be 0.0905. So it can be either positive or negative, okay? So for a normally distributed curve like this, okay, where you have 3 standard deviations within the curve, right? For each standard deviation, it will increase by 0.0905. Okay, for each unit of standard deviation to the left or to the right. Please, are you okay with this?
Yes, please.
So if that is the case, then administration would like to know the probability of obtaining a sample proportion that is between 0.55 and then 0.65. Okay, so this number has been given to us. So the administration would like to know the probability of obtaining a sample proportion that is between 0.55. So written mathematically is the probability into brackets. Okay, we're looking at a sample proportion that is more or equal to 0.065. Okay, or less. Sorry, we're looking for the one that is between 0.65 and then 0.55. So we have the upper value and then we have the lower value. So like we did for our first calculation, we can calculate the z-score for the upper. Okay, so the upper here is 0.65 minus our sample proportion of 0.567 divided by our standard error of 0.0905. That gives us 0.92. And then we calculate that for our lower two, we get negative 0.19. Okay, so we go to our cumulative, our z-score table, and then pick out the probabilities from there. Okay, and we find a difference that gives us 0.3956. So the interpretation here is that approximately 40% of sample proportions are between 0.65 and 0.55 if we collected more samples. If we collected many samples, that would be our interpretation. Yes. So,
hello,
yes.
Nana.
Yes.
Can we go back to
our previous slide? But are you okay with this?
Yeah, I'm okay with it. I just want to confirm something. The next one.
Back. Are we okay here?
In the previous one, you said if x over n is less or equal to 0.05, we use the infinite formula. But if it's greater, we use the correction factor. Am I right?
Yes.
Yes, but we are getting. Okay, and the question, the example you just gave.
Because here you do not know the entire population of people on campus. We've just been given small n, that is 30.
Okay.
Have you seen? So where you have, normally you don't know the entire population. Okay. But even if you get to a situation where you know the entire population, let's say we can know the entire population of PNUST. Okay. And then we go and then interview 30 people. In that instance, you do the n over small n over capital N. Okay. But where you do not know the entire population, just stick to the one on the right.
Sure. Okay. Thank you.
Yes. Yeah.
Yeah, Nana, please. Yeah, to this slide, this particular slide. So, with the first standard deviation is yes, sir. If you add 0.0905 to 0.567, you are getting 0.6575. So normally are these approximation values that we are using in examples, we approximate, like how do we go around it?
I don't get you.
Like the graph, the charts there.
Yeah.
If you add the proportional value 0.567 to the standard error 0.0905, the first standard deviation is going to give you 0.6575 instead of the 72. That doesn't cause a problem for us when in an exam we are doing something and we approximate, like we get different values like that. We just okay.
Yeah, we've taken the whole of the approximations and then added it to it. So that's fine.
Okay.
If you are approximation to the personal it's fine.
Okay. Okay. Okay.
All right. Any other question? Any other question? Okay. So, yeah, so we pick the upper and then the lower from our T table, and then we get that. We get, right? So, everything is worked out here for you. Right? Okay, let's see this question. So let's develop this argument a bit further. So the administration of Analytics University is considering adding a Moonlight Cafe to the chain of restaurants on campus. The cafe will have drinks, snacks, comfortable furniture, and plenty of study space. To learn more about the student interest, the administration has a BBA graduate student to go out on campus and survey 30 students. Yes or no? Would you like to study at Moonlight Cafe at least once per week? If it can be estimated that at least 60% of the student body will answer yes, Analytics University will go ahead with the project. So the Analytics University has set out this threshold that if we can estimate, okay, if the probability of students that say yes is 60%, okay, then we'll go ahead and then establish the project. So let's see how we can go about this. For the Moonlight Cafe, 25 graduate students, workers are tasked with contacting 30 students to ask each of them demographic information, primary survey question about the cafe. In the end, the researcher will end up with 25 samples of each containing yes/no responses for 30 students. Okay? So here we are interested in the answer response yes. So the number of yes response is the quantity of interest. Okay? So what we need to take into consideration is that let's assume that we do not know the whole population, or there wouldn't be time to interview the whole population. Therefore, we need to take samples, okay, and then make inferences about the whole population. Okay, all right. So let's see how. So these 25 people have brought their results. Okay, so the first sample, 22 people said yes. Okay, let's go column wise. Okay. So the second sample, 17 people said yes. Third sample, 15 people said yes. Fourth sample, 14 people said yes. Fifth sample, 18 people said yes. Okay, to all this. Okay, so these are the results. Basically, sorry, these are the results of the 25 people. Okay, so sorry, it's not the sample, it's the students. Okay, so for each of the students, okay, it's basically the same thing. So each of the students, the results that they brought is 25. So the students interviewed 30 people each. Okay, but we are interested in those who said yes. So for the first sample or the first student, okay, 22 people said yes, and so forth for the 25 students that we have. Okay, so these are the variable of interest. Okay, so let's work with this. Now, in order to determine the sample population, okay, or sample distribution for the proportion, okay, for each of the samples, all right, remember, so the first one, 22 out of 30. Can you calculate 22 out of 30 and let us know the sample proportion? Can somebody do it quickly?
0.733.
Okay, so that's what we have for the first sample. Okay, so 0.333. Okay, for the second sample is 17 over 30. That should also give you 0.5666. So all of them over 30 should give you this sample, corresponding sample proportions. Okay, are we okay with this? So let's say 18, let's say 1, 2, 3, 4, 14 over 30. You compare 1, 2, 3, 4, 14 over 30. If you do it, it should give you over 30, it should give you 0.4666. So for each of the samples, we've calculated the sample proportion. Okay, are we all okay? We've done this for the 25 samples or 25 students. Are we okay with the sample proportion?
Yes.
Okay, so let's go on this. All right. So the expected population, we have said that if 60% of the people say that we will say yes, then we'll go ahead. Okay. So we use this as the expected population proportion. That is 60%. That works out to be 18 over 30. Okay. So we use this in calculating our standard error. So we know that our P is 0.6. So in calculating the standard error is P into bracket 1 minus P over N. And our P is 0.6. Okay, 1 is given. So minus 0.6 divided by 30 gives us 0.8944. All right. So what happens here? So here we can now do our Z-score. Okay, so our Z-score is 0.6 minus the mean. If you take the mean of all the sample proportions, okay, you add all the 25 up and then find the mean. So you add all the sample proportions and divide by 25, you are going to get 0.612. Okay, so that is our expected value, okay, of all right, so when you do that, you divide it by the standard deviation. That gives you negative 0.134. All right, so we go in to check our, how do you call it? We go and check the cumulative probability. Okay, remember that we are talking about at least 60%. So whatever you read, if you go to the T table, for instance, okay, and go to the T table. We are looking for, sorry, we are looking for negative 0.134. Okay, so let's go to our T table. Okay. Okay, so negative 0.13. Is it negative 0.134?
Yes.
So what are we getting here? have negative 0.13. Negative 0.13. Is it this? Let's check this.
Yes, that's it.
That's it. Okay. All right. So if we come back to okay. So since we are looking for, so it's 0.4483. So since we are looking for a probability of at least 60, we deduct this, okay, from 1, and it gives us.
Please, we can't see your screen.
Oh, sorry. Sorry. Okay, so since we want at least 60, then we deduct the 0.4483 from 1. That should give us the result for at least 60. Okay. All right. So what we are saying is that based upon our calculations, 55% of the students, we have estimated that 55% of the students, okay, say yes to the to re-establishing the restaurant. But from the onset, we said that if 60% of the students say yes, we're able to estimate 60% saying yes, then we'll go ahead with the restaurant. So should we go ahead with the restaurant based upon our calculations?
No.
No, sir.
No.
Okay. All right. Okay. So basically, that is, we've used sample proportions to be able to answer the probability of students giving a response to our variable of interest. Okay. Yes, Francis.
Yeah, Nana, please, where from the one that we deducted the 0.44 from? Why do we deduct from 1?
Okay, so what we've done, the probability that we calculated, you understand how we got the 0.4483?
Yeah, very well. So I think that should be the final probability. Where do we have?
That's the probability for 60%. Have you seen? But we want probability for at least 60.
Oh, okay. So it must be below 60. Okay. Yeah.
So we have to deduct it from 1, and then we get the upper.
Okay. So Nana, above 60. At most 60. Well, how would that one be? Would you add it to 1?
At most 60. Okay, so if at most 60, because what we've calculated is up to 60 here, 0.4483.
Okay.
So that answers it. Okay, so any other question? So we've looked at situations where we have sampling distribution for proportions. Okay, here we are only interested in our variable of interest. Okay, we are only interested in our variable of interest. We are not interested in other thing. Okay, so we use that to be able to establish our probabilities. Okay. Yes, Stephanie.
Nana, please, could you go back? And please,
Yeah.
and please back. Where we have the expected value of P, yes, please. Please, could you explain that? I don't really understand.
The first one.
Yes, please, the expected value of P, yes.
Okay.
I know the 30 is for the 30 is for the number of information that's like was being gathered, but I don't know what the 18 is for. So if you could explain it.
Okay.
Thank you.
So in the question said that if 60% of the students, if at least of the students will go ahead with the project, okay?
Yeah.
So percent of the 30 gives us 18, isn't it?
Pardon?
60% of the students gives us 18.
Okay.
So that's where we started to work with. So that was like our threshold that we were working towards.
Okay. Thank you.
Yeah, Stephanie, your hand is raised. Okay, good. So, let's look at it. Key pointers. So the standard error of the mean, what we've done so far, the standard error of the mean is another name for the standard deviation of the sample distribution. Okay. The standard deviation also allows us to calculate the z-scores and therefore the probability under the curve for certain regions. Right? So any point estimator is just that, an estimate, and will therefore contain an error. Yeah. This error can be minimized by selecting a large sample from the population from which to estimate a parameter. Okay? And also realize that as the sample size increases, the standard error also decreases. Any questions on what we've done? Okay. Any questions? Any questions? Okay. So let's, if no questions, then let's go for our long break now, and then we'll come back an hour's time. And then we'll continue.
Okay, no.
Yeah. Are we okay?
Yes, sir.
All right. So let's go and come back 10 past 12 or something. And then
Okay.
Hello, Nana.
yes.
Please, how long is the break?
Let's go for 1 hour.
Okay. Thank you so much. I'll revise. Thank you so much.
Okay. Don't go and eat heavy. And come and okay.
Thank you, Nana.
See you soon. Okay.
Some people are dozing already.
Right.